explicit. Why do we know these are explicit definitions? Thank you. That's very important. Why do we know that these are explicit definitions up at the top? A, B, C, D, E. Why do we know they are explicit definitions?
Because it does not depend on
previous terms. It doesn't depend on previous terms. There's no S sub n minus 1 or S sub n minus 2, S sub n minus 3. They don't depend. So if you wanted to match these, right here, what would you need to write out for each of these? What would be helpful to write out?
a few of the terms.
A few of the terms, right. So for example, let's just do A. Starting with 1. 2 minus 1 over 1 is 1, right? So what does that automatically limit this answer to? It automatically limits it to what? 2 or 4, right? So you're automatically to 2 or 4. Then what happens? Then it's minus 1, minus a half, minus a third, minus a fourth. So what is it doing? It's getting closer and closer to what?
2.
It's closer and closer to 2. So which one is it?
2.
2, right. So then you can do the second one here. Oh man, what's going on here? What does that negative 1 to the first power do? It flips it, right? It's going to go boop, 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 boop. And this thing is going to get smaller and smaller, right? So basically the center is going to get smaller and smaller, but it's going to oscillate eventually around, like as this goes to infinity, this goes to 0, right? That goes to 0, and this thing goes positive 2, negative 2. Oh, negative 2, positive 2, negative 2, positive 2. So which one is it? Which one is it? Is it this one? No, negative 2, positive 2, negative 2, positive 2, right? Yeah. So it's going to go 5. It's going out from it, right? It's going out from it. Does that kind of make sense? Oh wait, but this side is the wrong side, isn't it? Yeah. Because you're adding it every time, so which one does it have to be? 3. Does everybody see what's going on there? So this logic, you need to remember not to forget straightforward logic. At the same time, don't get too detached from writing numbers down, because if you don't write the numbers down, you go, oh, it's obviously 5. Look, it can't get less than negative 2, right? It has to be to the right of negative 2, because you're adding the 1 over n. Does that make sense? Mm-hmm. What about C here? Oh, it's 2. It's going to be centered around 2. And it's going to oscillate around 2, so we get closer and closer to 2. So which one is it? 4. And then eventually you process of elimination, and unless it's lying to you, you're done, right? So use logic. Use logic, but don't forget to write out numbers. Don't forget to write out numbers. Because, for example, on the AP test, do they give you evil answer choices? Yes. Yes. It is arguably one of the most tested demo tests you'll ever take in your life. So what do they do to choose false answers? They have like 1,000 people do the question, come up with the correct answer, of course, but then find what the most like common 4 other answers are. Like if you tweak one, you're like, oh, it's obviously right because my number is there. Careful. You still want to actually answer the question, of course. Okay, so this is what we're going to be working with today right here. You've already looked at this one maybe. It was the first example in there. Each of the following infinite geometric series, for them, find several partial sums and if the sum exists. So what's the difference between a series and a sequence? A sequence have what between the numbers? Or the items, yeah, the elements, commas. There's now an operation. How far can a series go? Well, keep going, right? Or you could stop, in which case it is a finite. So a series here has pluses, has an operation between them. Does it always have to be plus? No, like in C it goes minus, oh, it doesn't have to be the same operation, right? So what are we going to be looking at? What happens when we add up some of these terms? What happens when we add up all of them? Some of them can be done by logic, but you need to look at, first, for example, partial sums. What is a partial sum? Do you remember from your notes? What's a partial sum? What's partial mean? A piece of, right? So if we were looking for what this whole thing adds up to, if we think goes towards infinity, we could see if there's a pattern of the partial sums. The partial sum. So what's the sum of the first term? So just 1. So if we have one term, what's the sum? 1. If we have 2 terms, what's it going to be? 1 plus a half, which is 3 over 2. 3 terms, what's that going to be? 1 plus a half plus a quarter. So that's going to be 3 over 2 plus a quarter. So what's that going to be? 13? Come on. Come on, fractions. What is it? 7/4. Thank you. That's so nice. 7/4. Nice. What about 4 terms? Well, that's going to be 1 plus a half plus a fourth plus an eighth, right? So that's going to be 7/4 plus an eighth. So what's that going to be? 15 over 8. And could we keep on going with this? Could we keep on going with this? So 1 term is just 1. 2 terms added up is 3 over 2. 3 is 7 over 4. 15 over 8. Anybody want to guess what the next one's going to be? Anybody want to just guess? Just guess what do you think 5 is going to be without doing any of this. Do you see a pattern? What'd you say?
31 over 16.
Looks like it's 31 over what? 16. That's a great guess. What about 6?
63 over 32.
32. You keep on doing this, and if you assume that's the pattern, which you can eventually prove, do you have an idea of what this is going to? So what do we think if we went all the way, like the limit, let's call this the iteration here, as n goes to infinity? What do you think it's going to be? What are those numbers getting, what does it look like they're getting closer and closer to? Yeah, it looks like they're getting closer and closer to 2 from what side? The bottom or the top? The bottom. It looks like from, not plus, minus. It looks like you're approaching it from the bottom. It looks like you're approaching it from the bottom. Is this a proof?
No.
It is not a proof.
Isn't this like square?
Hold on, this one sec. That this is a geometric series because 2 over 1 is equal to 4 over 2, which is equal to 8 over 4, right?
Yes.
Now, what are the partial sums here? 1 is 1. What's 2? 3. Sorry, not 4. I'm going up too fast. 3 is 7, and 4 is 15. So for this one, I could ask you, what do you think this is converging to? Is it convergent?
No.
No, this is definitely, based on what we see, what?
Divergent too.
Divergent. Not a very good movie. Okay, moving on. What about this one? Is this, first of all, a geometric series? Is this? How do you know if it's a geometric series?
There's a common ratio.
Common
Constant
ratio. That's fine. Seema, what is the constant ratio in this case? What is the constant ratio? What do you do to 6 to turn it into that 2 to 2/3, 2 to negative 2/9? What's the ratio? Close.
Divide by 1/3. I don't know.
Divide by negative 3. So the ratio is what? What is the ratio on this one? What's the common ratio? Negative 1/3. The ratio is negative 1/3. The ratio is negative 1/3. So let's just test this out. The first partial sum is 6. The second partial sum is 6 minus 2, which is 4. The third partial sum is 6 minus 2 plus 2/3, which is 4 plus 2/3. I like improper fractions. I really like improper fractions. So what's that going to be? 14/3. I do not like this. Do not do that. I hate that. Hate it. Don't. No. Write it like this, please. Also, if I make small math mistakes, please correct me. Don't wait 5 minutes and then laugh later when we fail. 4, what's that one going to be? 6 minus 2 plus 2/3 minus 2/9. What's that going to be? 14 over 3 minus 2/9. To add or subtract fractions, what do you need? Common denominator. So what's our common denominator going to be? 9. So what do you get here? 52 over 9 minus 2 over 9. So what do you get? Oh, 40. See, look at that. There's that small mistake I'm making there. Man, I'm on a roll. So what do you get? 40 over 9?
Yes.
So let's do one more here. I think we have another term written up there, right? We have 2 27s. So what's 5 going to be? 6. It's all of them, right? 2/9 plus 2 over 27. What's that going to be? 22? Oh, you did it already. You're just doing it out already? So it's 2 over 27. So we multiply 3. So 120 plus 2 over 27. So what is it? Over 27. So if we wanted to get an idea of what this is approaching, what could we do? We could look at this. We could look at the sequence of partial sums. The sequence of partial sums. So what is the sequence of partial sums going to be on this? It's going to be 6, then what?
4.
Then 14 over 3, then 40 over 9, and then what? 122 over 27. Now, if we wanted to make a guess, fractions are a little challenging to work with, so we could put it into decimal. I generally don't want things in decimal form. Could someone just tell me the decimal forms if you have anybody have a calculator? Thank you. When I say we have a couple people could do it, so we check each other. So we have 6, 4, what is that? 4 point what?
4.66.
Repeating, right? And then what do we have here? 4.4 repeating, and then what? 518 like this? So it's above, and then it went down. 518, 518? Is it 518, 518, 518, 518, or just Got it? Like this? So the 8 is repeating too. So does it feel like this is converging? Does it feel like this is converging? What do you think? Do you think that this so this went down, right? And then what did it do? Up, and then it went down, and then it went up. But it's oscillating less and less, right? Because what is it changing by? Negative 1/3 every time, right? Oh wait, what did we forget here? Oh no, the partial sums go up and down, but this is still positive. So do you think that this is getting closer to one specific number? What do you think? The partial sums are going up and down.
You're always adding something, though.
Yes, you are. You are always adding something here too, but we think it's going to go eventually to 2. It's going towards 2. Do you think that this is going towards a bullseye is what I'm saying? Based on what you see right here, do you think that that's going towards a certain bullseye right here? Yes. Does it feel like it is? It feels like it is because the partial sums are they're oscillating by less and less, right? The oscillation is less and less. Now, is it clear? And that's a terrible math word, remember? I think I talked about it yesterday. Did I mention that? Clear is terrible because either you see it or I'm saying it's clear and you're like, I don't see it. Like, I've literally been like this close to things. Just because you're this close to them does not mean you can see it. Like if I'm right here, what do I see? I see a lot of movement. I don't see a person, right? Same thing here. It might be clear. We could do a few more. We might guess. What do we think our guess should be? If you had to guess, what do you think it could be? Just take a wild guess. What do you think this is converging to? Do you think? Just take a guess. Is it 7? No. It has to be between what and what at this point? 4.44 and 4.518. It has to be between those two. The difference is getting smaller each time. It has to be some, I don't know, let's guess 4.5. Sure. Right? Maybe it's a little less than that, but that could be a guess, and that would be a reasonable guess. Okay, but here's the thing. In math, the difference between being pretty sure and proving something, the difference between 99% and 100, sometimes we think that's not much, right? But in math terms, it's everything. Here's the operation. Go halfway to the wall. I 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 go halfway to the wall. What is the limit of that operation? The wall is the limit. Do I ever get to the wall? No. No, but can I get arbitrarily close to the wall? So if Tomas says 1 millimeter, at some point, am I going to be within 1 millimeter of the wall? Sure. Yes. So therefore, no matter what Tomas says, a millimeter, a picometer, a billionth of a picometer to the negative whatever, can you always get that close? Sure. Yeah. That's what this is saying. It's saying the limit is L if no matter how close you want to get, you could always get that close. So a horizontal asymptote, when you draw it, for example, it is a horizontal asymptote because the function gets as close as you want. It's getting closer and closer and closer. So if you say 1/10 of an inch, you can get that close. And you need to usually be able to tell how many ways. Now, if you can't, it's not the limit. So if I put a wall up even a millimeter from the wall, can I always pass that? If I'm going halfway to the wall and halfway to the wall and halfway to the wall, if I put another barrier right here, is this the limit? Because I can go past it. I can go past it. If you can go past something, it's not the limit. Technical math definitions, is this poetic? Not so much. Is this 100% correct? Absolutely. It's much more important right now that you understand the general idea than it is to be able to write down each individual word. Okay, so here is the first fact for you. You remember this maybe from your notes. To calculate the limit of a sequence, we use what we know about the limits of functions, including the properties if they're 1.2, and the following facts. The sequence Sn to the x to the n, so x squared converges if x is less than 1, and it diverges if x is greater than 1. So this one right here, Sn, do the following sequences converge or diverge? A sequence, remember, there's no addition here. So what's the first term? N is 1. What's the first term? 1/8, right? So not 1/8, it's 80%, like 0.8, right? 0.8 to, and if you square 0.8, does it get smaller or bigger? Smaller. It gets smaller. If you cube it, does it get even smaller? Yes. Yes. So does this sequence converge? Yes. Why does it converge based on what you have above? The absolute value of 0.8 is what? It's less than 1, so therefore it what? Converges. It converges because the absolute value of 0.8 is less than 1. Let's just jump to C because I kind of like this one. Does this sequence converge? Why not? Why doesn't it converge, Tomas? Yeah, what is S sub 1? 0. What's S2? 2. What's S3? 0. What's S4? 2. If you get stuck in a loop, does it converge?
No.
No.
It's kind of like sine functions, no.
Exactly. Does sine converge? No, it doesn't. Infinite oscillation. But this one will just be beep, 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 with the sound effect, of course. What about this one? How would you analyze this one? Any idea what you should do to analyze this one? Any ideas of what could you do? Yeah, so let's just do this. So this is e to the n, right? 1 plus what? E to the n. And we'll do a little bit of hand waving right here. As n gets infinitely big, which pieces should we look at? Let's look at these pieces right here. Exactly. What's the limit as n goes to infinity of 1 over e to the n? 0. So those things are going to 0, right? So therefore, what does this partial sum equal? Not the partial sum, the sequence goes to 1 over 1, which is 1. So this one is, I'm putting this one in there because don't forget basic algebraic manipulation. I can take something that's really straightforward, change it just a little bit to make it look more complicated, but then if you simplify it and look at pieces, oh, 1 over 1 is 1. Okay, and in this section of the book. They're adding series, but what type of series? Geometric series. Do you see a geometric series? Yes. Why? Why do you know this is a geometric series? Common ratio. What is the common ratio? 0.04. How do you go from this term to this term? You multiply this by, or backwards 0.04. So the way you can see it is the common ratio is 0.04 to get between them. So what did I do to get from this line to this line? I didn't divide it. I put it out there. What did I do? What did I do to get from this line to this line? Be careful. I multiplied it by 0.04. Why did I do that? Anybody want to know?
Get rid of the negative.
I just didn't want that negative one up front. That's fine. And then what did I do? Oh, look at this. It was 0.04. Okay, so if we want to know how many there are, what the amount of drug after 10 dosages, what do you plug in for n? 10. So I plugged in 10 to the first one. So you can ignore this for now. Ignore that for now. But I plugged 10 into the first one. So Q10, 250 to the 9, 8, all the way down to 250. Right there. Now, here's the thing. Could you theoretically plug this entire thing into your calculator? Sure. You could plug this entire thing in your calculator. Do you want to do that? No. Not so much. You really, really, really don't. So we end up with Q sub n times 0. What? Minus 1 is equal to, what can we factor out up here? 250 times 0.04 to the n minus what? 1. And then how do they get from that red to what we have is almost identical, right? What's the only thing that's different? Yeah. If you flip this, what do you have to do with this? Flip that. Does everybody see that? You flip this and you flip that. Why is this super nice? If we want the concentration after 10, we just plug in 10 into this. Is this a lot easier to use than adding up all 10 terms? Yes. Let's dilate it out. What happens if it's 1,000 terms? We'll just plug in 1,000, right? Hey, what can we answer? We now have an explicit definition for the partial sums. The sum of the first n. This is the definition of the partial sum. So we can take it as n goes to what? Infinity. Let's say we took this drug every 6 hours for the rest of our lives. We're going to get closer and closer to what? We run a limit on this. Could you run a limit on this? You sure can, because here's the thing. If n goes to infinity, what happens to this? It goes to 0. Why? The absolute value of that is smaller than 1. This is 0, so you get 250 over 0.96. Do that for me. What's 250 over 0.96? Someone do that on their calculator, please. What is 250 divided by 0.96? The limit as n goes to infinity of qn is what? 200 and what? 200 and? Okay, Tom, you say it. Go. 416. So what does that mean? If you kept on taking this until the end of time, that's what you would end up with. So all of that is...
you multiply by 1/2?
Yeah, so the ratio is 1/2. What's the a value?
Is the a our initial value?
Yep.
That's 1.
1. So let's just test this out here. So we said Sn is going to be equal to 1 times 1 minus, what's r?
1/2.
1/2 to the n, all over 1 minus 1/2. Well, if n goes to infinity, what does this do? 0, so you're left with 1 over 1/2, which is
2.
2. Boom.
It's gonna have 2.
Exactly. Is that what we thought it was?
Yes.
The only thing we haven't done to quote-unquote prove this is, I gave you specific numbers. What was the specific starting value? 250, right? Could I have replaced that with A? Yes. R, instead of 0.04, I could just write R. And would you end up with this formula? Yes. So let's go back down here. What about this one? Too far. What's the ratio here? 2. What's the A value? 1. Does this converge? No. Why? Yeah, the ratio is bigger than 1. What happens if the ratio is 1?
Well, it's the same.
Same number over and over again. Does that sum converge?
No.
No. Oh, what about this one? What's the ratio? What's the A value? 6. So what do we have here? Sn is going to be 6 times 1 minus negative 1/3 to the n all over. Yeah. Like that? Like this? So if we wanted to do n goes to infinity, that would go away and you're left with 6 over what? Which is 6 times 3/4, which is 18 over 4, which is 4.5. Was that our guess? We're so good at this game. We're so good at this game right now. I'm so happy. So happy right now. So going back to the specific numbers and how this is grounded in reality. Another way this is grounded in reality is saving, which is pretty cool. Number 1, is it geometric?
Yes.
Yeah, what is the ratio? Ratio is -2.
Oh, it's frozen.
Oh, it's frozen. Thank you. I'm doing that a lot today. It says, for those which are, jumped up there, sorry. Give the first term and the ratio between the 6. So what's the A value? 5. So you can just circle all these A values. So regardless of if they're geometric, those are the A values, right? Those are the A values. So you have, what's the ratio for the second one?
It's 1 over 10.
Oh no. Okay, so is this one not geometric? What's this one called, Tomas?
Harmonic.
This one's really cool. Does this converge? It actually doesn't. We'll talk about that later. Here's a side note. Does the alternating harmonic converge? 1 plus 1/2 minus 1/3 plus 1/4? It's pretty cool. What about this one? Is this what's the ratio here? 1/2. What's the ratio here? Nice. And what's the ratio here? It's not geometric, is it? Why? It's so close, right? You want to make the ratio x?
But it doesn't work.
But it doesn't work because of the numeric coefficients. 2 to 3 is not 3 to 4. Good. That's all you needed to do. Okay. Get up to the board, everybody. Get up to the board. You can erase there. Let's get groups over on the sideboards. Please do 14 through 17. I gotta do that. Thank you. Unfrozen. Okay. First one. What's the ratio? I think it's 1 over 2, right?
Yes.
What's the ratio here? Negative 1/2, right? And what's the ratio here? 1/3. And what's the ratio right here? 1/3. Excellent. So you have ratios. They're nice. They're all absolute value less than 1, so maybe they do something nice. So for this one, the sum of the first n is going to be the first term times what? 1 minus what? 1/2 to the n all over. Yeah, and that one's finite. It ends. What's the last term you have to plug in? This is the key to this entire problem on this one. N equals what? Is it 11 or 10? If 3 is 1, then this has to be, so that's 2, 3, 4, all the way to the 11. So it has to be n equals 11 on that one. Be real careful. So you plug in 11, and then can you do that one without a calculator? It might be a little challenging. So the S11, what's that going to be? 3 times 1 minus 1/2 to the 11th all over what? What's it going to be really, really close to? What's it going to be really close to? Come on. What's it going to be really close to? 6. It's a little less than 6, right? A little less than 6. Nice. What about this next one here? That one's going to be what? Sn is equal to what? Help me out. Sn is equal to? Negative 2 times 1 minus to the n all over
1 minus 1.
negative 1/2, right? Nice. So that's going to infinity, right? So what's that going to be? If n goes to infinity, what do you end up with? Negative 2 over what? 3 over half. So you end up with negative what? 4 over 3. Yay, exciting. Infinite geometric series right here. What's our first term? What's our first term? 1 over 3 to the 4th, because where's n starting?
Oh, 4.
That's a really cheap thing for the book to do. It starts at 4 instead of 1. Just be careful, that can't happen. So if that's our common ratio, we know Sn is going to be 1 over 3 to the 4th times what? 1 minus to the n all over 1 minus 1/3. So what's that going to end up being if you had s as the limit as n goes to infinity? The limit as n goes to infinity of Sn is going to be 1 over 3 to the all over 2/3. So that's 1 over 81 over 2 over 3. 1 over 81 times 3 over 2. What is it? Thank you. Nice. Now, what's the annoying thing about this one right here? Well, annoying, I'll put in quotes. What do you think? Starts at 4 and ends at 20. You just have to be really careful about this. It starts at 4 and it ends at 20. So what are you actually calculating here? You're calculating S20 is going to be 1/3 to the 4th times 1 minus 1/3 to the what? To the what? Careful here. What do you put it to? Do you put it to the 16? N equals 4 all the way to 20. Which one is it? Remember what we did to prove the geometric series? What did we multiply both sides by? The common ratio, right? Do you remember this? I understand, but hold on. The sum of the sum we're looking for from 4 to 20. So what did we multiply? We multiply by 1/3. What did that do to each of these powers? It increased it by 1, right? Correct? 1/3 to the 6 to the what? 7th all the way to what? 1/3 to the what? 21st. And then we subtracted that one from the bottom. So what did we end up with? 1/3 S20 minus S20. What was that equal to? 1/3 to the 5th minus what? The 21st, right? Are we doing okay so far? So then we had S sub 20 times 1/3 minus 1 is equal to 1/3 to the 4th minus what? Oh, sorry, 1/3 to the 4th. What's in there? 1/3 minus 1/3 to the what? Come on, if I factor out what's up here? It should be on the 3rd. Which one? Hold on, one at a time here. Sorry. If we factor out 1/3 to the 4th, what do we end up with in here? 1/3 to the minus 1, correct? And can we flip those around? So what do you end up with S20 being? 1/3 to the 4th, 1 minus 1/3 to the 17th all over 1 minus 1/3. So is it indeed 17? We also could kind of see that in the first one, because what did we have to start with here? N equals 11, like kind of like 1 greater than the index that you plug in. Okay.